In this video, I'm going to run through revision of CC5 and CC6, which is ionic and covalent bonding, and then we've also got CC17, which is the topic that we're doing at the moment on the atmosphere. Quite a lot of this, I would say, is pretty straightforward. Even if you don't know an initial answer, when you have a look at the mark scheme, it should hopefully be quite clear. So I'm going to keep this video pretty short. First question. It's just a definition: shared pair of electrons. You need to say pair. Why is it a gas rather than a liquid? If it's a gas, just remember the particles are really far apart. If they're far apart, it's because the forces are very weak. So you need to tell me that there are weak intermolecular forces. That's the only type of weak force we learn about. Weak intermolecular forces, it doesn't take much energy to separate those molecules. We did this recently. The test to show that a gas is oxygen. A glowing splint is going to relight. So a glowing splint would be a splint that was on fire. A splint is just a piece of wood. So it was on fire. You put it out. It's still kind of glowing red hot. Then you put it into oxygen and it relights again. That's your test for oxygen gas. This one I'll do. Write the electron configuration for the ions in potassium oxide. Okay, so if I look at the ions, potassium's in group 1, it's got a charge of +1. Oxygen's in group 6, it's got a charge of -2. Now potassium normally has 19 electrons. You'll get that from your periodic table. I'll just show you the numbers next to potassium are 39 and 19. So it normally has 19 electrons, but because it's +1 as an ion, it means it has lost one of those electrons and there are only 18 left. That means the electron configuration is 2 and 8 is 10, 10 and 8 is 18, okay? Oxygen, if I do oxygen, has the numbers 16 and 8 next to it. That means it usually has 8 electrons, but in this case it's an ion with a -2 charge. That means it's gained another 2. So it usually is 8, it's gained 2, now it's got 10. If it's got 10, the electron configuration is 2, 8. The next page, this is a 6 marker. It came up 2 years ago, and if you look at the booklet or even the textbook, this content is only a really small part of the course, and they asked a 6 marker on it, which threw off quite a few people. However, if we have a look, it's actually really easy to pick up marks, even if you haven't studied for this, by just kind of saying what you see. So you're asked what information can be obtained from each representation, and then to give the limitations of these representations. So it's methane, it's CH4, it's just represented in a few different ways, and for each one you can just tell me what information do you get from that representation and what are you missing. So if we just look at A, the only information I get from A is it tells me that methane is made up of 1 carbon and it's made of 4 hydrogens. So it gives me that information, but it doesn't show me how the atoms are arranged. Okay, if you knew nothing about chemistry, you might think there's a hydrogen in the middle and then a carbon up here and then another hydrogen to the side. It doesn't give you any information about how the atoms are arranged. It doesn't give you any information about bonding or the shape or the structure. It just tells you 1 carbon, 4 hydrogens. The next one's a bit better because it tells you 1 carbon, 4 hydrogens, but it also shows you how the electrons are arranged. So it shows you that carbon's in the center, you've got 4 hydrogens around it, and it shows you that there is 2 electrons being shared between carbon and each of the hydrogens. The next one again shows you that you've got 1 carbon and 4 hydrogen, shows you how the atoms are arranged, but it doesn't give you the information about electrons. This one, D, is better. Okay, I know it mightn't look quite as clear, but you've got the atom in the middle. You've got the 4 hydrogens coming around the outside, and it shows you that CH4 is actually 3D, and CH4 is 3D. So this is a better representation than what you had in C, because it shows you the 3D shape of CH4. The kind of downside to C and 4 is it shows bonds as these kind of sticks, which obviously isn't real, and it shows the hydrogen atoms being quite far away from the carbon, whereas E shows that 3D structure again, but it shows a better representation of the distance of the carbon from the hydrogen, so that's just a little bit more realistic. So I'll just show you what they have here on the mark scheme as a possible response to get kind of 5 and 6 marks. All right, this is a full like 6 marks. Okay, Model C shows the displayed formula and single bonds, but it's only 2D. Does not show the position of the atoms in space. Then it goes to Model A, just says it's the molecular formula, tells us how many carbon and hydrogens. Model D shows a 3D arrangement, but Model E does not show how the atoms are bonded. So you don't need to talk about each one equally. You just need to say ideally one little statement about each one, or at least one statement about 4 of the models, and you'll be able to get your marks. So it says here, to be in this range, gives a description of at least 3 models. Okay, so there's 5. If you talk about at least 3, you're okay, as long as you're giving limitations of each model you talk about. Or your other option is you talk about all 5 of them briefly, and then you only have to give 1 limitation. So there's lots of different ways you can write the answer. You can just pick the model that you're most comfortable with and talk about that in more detail. But there are lots of things you can say, and it's also on your carousel. This question here is on your carousel as well. We spoke about it in lessons, but I'll just go over it. Okay, so the point of this is you're trying to work out how much oxygen is in air. So we know in air around us in the atmosphere, we've got oxygen, we've got O2, we've got nitrogen, we've got O2, we've got some argon, we've got some CO2, and we learned percentages of these, and we learned that oxygen was 21%. But how do we know that? So what they do here is they've got a piece of zinc, and they would take the zinc and they would heat it, and on the left hand side you've got some dry air in a syringe, and on the right hand side you can see the syringe is completely pushed in. There's no air in syringe B at the moment. Dry air just means there's no water in there, no water vapor, but you've got nitrogen, oxygen, argon, CO2. And what you do is you'll push this syringe in, and the dry air will be pushed out over the zinc and into syringe B. And you'll see this part here, the syringe B, will push out as the air moves in. And then you'll push syringe B in, and you'll pass the air back into syringe A, and you'll push A in, and you'll pass the air back into syringe B. And you just keep doing that, passing the air over the zinc whilst heating the zinc. And what will happen is the zinc will react with the oxygen from air, but it won't react with nitrogen, argon, or CO2. And the zinc will react with the oxygen, it will form zinc oxide, and that will remove the oxygen from the air. And if the oxygen has been removed from the air, what you'll see is, let's say for example you started off with 200 centimeters cubed of air. By the time all the oxygen has reacted and the oxygen has been removed, you're going to have less air. Maybe now you only have 160 centimeters cubed. And when the volume of air stops decreasing and you're left with a constant, what you can do is you can subtract the final volume from the initial volume. So you see you've lost 40 centimeters cubed of air, and then get that as a percentage of your original volume, and you'll see, oh yeah, oxygen takes up 20% of air. Now, in order to get the marks, all you need to say is this, all right? So you heat the zinc, you pass the air over the zinc, you keep doing that until the volume stops changing, and then you just calculate the difference in volume. So you'll take the volume at the end and subtract it from the volume that you had at the start. A few dot and cross diagrams. So the first one here is O2. All right, so you need to know that oxygen is in group 6, and if it's in group 6, it's got 6 electrons in its outer shell. Okay, you only have to show the outer electrons. It's O2, it means I've got 2 oxygens. So there's 1 oxygen, there's another, and for each oxygen I've got 6 electrons to draw. So I'm going to be drawing 6 crosses, and I'm going to be drawing 6 dots. When you're drawing this, you need to work out where to put those electrons. Okay, this bit here in the middle represents the sharing space between the 2 oxygens, and atoms will always share the number of electrons they want to gain. Okay, so if oxygen has 6 electrons in its outer shell, it wants to have 8, because 8 is a full outer shell. It means it needs to gain 2 more. So it's got 6, it wants 8, it needs to gain 2 more, and if it wants to gain 2, it will share 2. So this oxygen is going to share 2 of its electrons, but it's got 6 in total, it's sharing 2, it keeps 4 to itself, and now this oxygen is done. I've drawn all 6 crosses. This oxygen is going to do the same. It's got 6, it wants 8. If it wants to gain 2, it will share 2. If it's sharing 2, it's still got 4 left over. Now, to check this, I need to make sure I've drawn 6 dots and 6 crosses, and I have. I need to make sure I've got an even number of electrons in the middle, and I need to make sure that every oxygen has 8 electrons by the end. So 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen. 1, 2, 3, 4, 5, 6, 7, 8. You get to count the electrons in the middle for both oxygens, so they do both have 8 full outer shells. The next one is another one, CO2, you're drawing, so you need to know that carbon dioxide is CO2. Carbon is in group 4, so it's got 4 electrons in its outer shell. It tells you that there. Carbon is 2, 4, that represents the outer shell. Oxygen, we've seen, has 6 electrons in its outer shell. So when I'm drawing this, the atom that's by itself goes in the middle, so carbon is going to go in the middle, and I'm going to have 1 oxygen on the right, and I'm going to have 1 oxygen on the left. And if I start off with oxygen, just because we've done it above, it's got 6 electrons, it wants to have 8. That means it is going to share 2 electrons because it wants to gain 2. If I'm using crosses, oxygen shares 2 electrons and it keeps 4 electrons to itself. This oxygen does the same, it wants to gain 2, so it will share 2, it shares 2, and it keeps 4 to itself. So I've drawn 6 crosses for each of my oxygen. Carbon, I'll use dots. So carbon's got 4 electrons, it wants to have 8. 8 is a full outer shell, therefore it needs to gain 4 electrons. If it wants to gain 4, it will share 4. So carbon is going to share all 4 of its electrons. And you've got 2 sharing spaces, and what it will do is it will share 2 with 1 oxygen, and it will share 2 with another oxygen. So if I do my checks, I can see I've got 6 crosses for each oxygen, I've got 4 dots for carbon, I've got an even number of electrons in the shared space, and I've got 2, 4, 6, 8 electrons, 2, 4, 6, 8 electrons for oxygen, and 2, 4, 6, 8 for carbon. You get to count the electrons in the shared spaces for both atoms sharing. Everyone's got 8 electrons. This should be relatively okay. The composition of the atmosphere, how it's affected by burning fossil fuels. When you burn fossil fuels, we looked at this, the combustion of fossil fuels adds carbon dioxide, and it also adds water vapor. So if we looked at the combustion of methane, for example, you form carbon dioxide and you form water vapor, so you're going to be adding that to the atmosphere. And then when you're burning a fossil fuel, you're using oxygen, so it's going to remove oxygen. So it's going to remove the oxygen from the atmosphere, and it's going to add carbon dioxide and water vapor to the atmosphere. The next here are graphs. I'm assuming it asks you a question. Yes. Explain whether these graphs provide evidence that an increase in carbon dioxide is causing the Earth's temperature to rise. So on one graph, you've got the concentration of carbon dioxide, and you can see that the concentration of carbon dioxide since 1960 has been steadily on the rise. If we look at the next graph, it's about temperature. You can see again, since 1960, it's a general rise up of around about 0.4 degrees Celsius. So you can actually argue either, okay, as long as you kind of back up your answer with evidence from the graph. So for one, you can say, as the concentration of carbon dioxide is increasing, that the temperature overall increases, but you can say that there's no evidence that this increase in temperature is caused by the increase in carbon dioxide. Yes, they're both happening at the same time, but there's no evidence from these graphs alone that there's a link between the two. The other thing they allow you to say is, as the concentration of carbon dioxide increases, the temperature increases, so this does provide evidence, so that they will allow you to say that too. So that basically they'll allow you argue either. You can say that they're both increasing and therefore they're linked, or they're both increasing but there's no evidence that they're linked. If you have a look at the mark scheme, it will kind of outline that for you, but just make sure you're referring to the trends in the graph. Describe the gases, carbon dioxide, methane and water vapor. Yeah, so these are your greenhouse gases, and it wants you to describe how the greenhouse gases keep the earth warm. So remember, a greenhouse, if you've ever stepped inside one, is incredibly warm. We call them the greenhouse gases because they make our earth feel like a greenhouse. They make our earth feel warmer, and the way they do this is that the sun, you know, obviously heats the earth. From a little diagram, this is the earth, this is the sun. We know the sun obviously heats the earth, so you can start off by saying just radiation from the sun heats the earth, and essentially the heat is going to be absorbed by the earth's surface, and then that heat is released back is released back, and usually the heat, when it's released back, just passes straight out of our atmosphere. But if you've got greenhouse gases, the greenhouse gases trap that heat as it is being sent backwards. So the sun heats the earth absorbs the heat, then the earth sends the heat backwards. But if you've got greenhouse gases, the greenhouse gases essentially block that heat from leaving the atmosphere and trap the heat inside the earth. The mark scheme is a little bit limited. There's only 2 marks for this, and they give you 3 points. So you can say radiation from the sun heats the earth. You can say the gases absorb the heat radiated back from the earth, or you can say heat is released back to the earth. So something implying how those gases are working. Which of these are both greenhouse gases? Your greenhouse gases are water vapor and methane. And that's the end of this quiz.